We started yesterday. That makes more sense.
Let's go, dude. Let's go. Hey, brother.
Alright guys, let's take a look at page 269. Yesterday we introduced our sixth and final graphical characteristic for these rational functions. We were talking about horizontal asymptotes, and we were discovering how the degree of the top and bottom of a rational function dictate or kind of signify or tell us some information about the location of a horizontal asymptote. Can we, just for reference, can we discuss those three different options that we had yesterday? If we're comparing the degrees of the numerator and the denominator, we have three different outcomes. The top can be less than the bottom, the top could be greater than the bottom, and the top could be equal to the bottom. Can we roll through those three cases and think about what they tell us about a horizontal asymptote? Yeah.
If the top's less than the bottom, then the horizontal asymptote's on y equals 0.
Forever and always. Okay, so if it's bottom heavy, okay, meaning the bottom has the higher power, then you'll forever and always have a horizontal asymptote at 0. What if we switched it, though? What if we had a top-heavy function? Go ahead,
It would be a slant asymptote.
Laney. Slant. Okay, so no horizontal, but slant. And what if they were equal? Yeah? Dividing coefficients. Okay, so we do have a horizontal asymptote, and it's going to end up being y equals a number. Okay, something other than 0, though. So y equals a number, and we do this, we figure out the number by dividing the leading coefficients. Okay, so we rolled through those options. Now, of the three options, we paid a little bit more attention to this middle one yesterday, like if we had a slant asymptote. Because the other ones are pretty simple, it's either 0 or a number. The slant asymptote, though, could be an equation. How did we figure out the equation of a slant asymptote yesterday? If you only had the function of a rational graph, how can you figure out the location of a slant asymptote? Yeah? Synthetic division. Okay, so we synthetically divided. Once we were done with synthetic division, where did we have to look to find the equation of the slant asymptote? What did we have to pay close attention to? Maybe reference the two examples from yesterday on page 260. You have an idea, Grace? Yeah.
The slope.
The slope? Okay, so if I look at... Or were you thinking about one from yesterday for the slope?
The top one.
The top one? Okay. So if we had the graph, we would be able to figure out the slope, which is good. What if the graph wasn't there and we did synthetic division with the function? After you do synthetic division, where can you find the equation of the slant asymptote? So the slope would be in there somewhere. Where did we have to look in our synthetic division setup? I think yesterday for this example, based off the graph, we found the equation to be x plus 4. Where did the x plus 4 show up in our synthetic division? Good, Lainey?
It was the first two numbers of the synthetic dividing. So, like, if you rewrote the equation, it would be x plus 4.
Okay, so once we got done with the division, the quotient numbers, like the numbers at the bottom, that's where we found the slant asymptote equation. So we'll say, look at quotient numbers for slant asymptote equation. Okay, only the quotient. We ignored the remainder. That only tells us if we have a factor or not. Okay, we just look at the remainder piece, or the quotient values. Now, when we noticed that little pattern yesterday, we went on to try to do this second example, and we figured out the equation based off the picture, but after we did synthetic division, we noticed how the quotient values didn't really match the line that we had here. There was something a little bit more we had to do. Yeah? Okay, so we have to be careful. If there's a leading coefficient in the denominator, we have to divide the quotient values by that number. Okay, so we're going to add that in here. Divide values by denominator leading coefficient. All right, I think that's a good summary of kind of where we ended off yesterday. So today we're going to pay a little bit more close attention to these slant asymptotes, or just horizontal asymptotes in general, and then we'll take a look at some kind of free response questions that bring all of these characteristics together that we've kind of been talking about since day one. Okay, so in this box, though, that's left, we're going to try to first of all determine if we have a slant asymptote or not, and if we do, we're going to try to find the actual equation of it. So we don't have a graph to go off of for these like we did yesterday. We're going to have to kind of trust our gut as we go through the division process. Okay, so take a look at the first one. Can we determine if we have a slant asymptote or not? Can we narrow it down? Do we have a horizontal asymptote at 0? Do we have a slant asymptote? Or do we have a horizontal asymptote somewhere else? What do you think, Caitlin? Why?
Because the top has more on it, so it's
Top heavy. Okay, so the top degree is bigger than the bottom. We have a 3 over a 1. So that's telling us that we don't have a horizontal asymptote, but we do have some type of slant. Okay, something that's not exactly horizontal. So let's go ahead and go through our synthetic division, look at our quotient, and maybe determine what that equation would be. So in this synthetic division process, we got to think of that special number, that one number that goes on the outside. Can we think about what that might be based off this fraction? Yeah? 1, where'd that come from? The denominator. Okay, the number that makes the bottom 0 in this case. So then we'll take the coefficients from the top, but we kind of have to be careful. With synthetic division, we have to make sure we go in order, and notice how we jump from a cubic term to a linear term. We're missing that x squared in the middle, so we're going to have to put in a 0 placeholder. All right, so let's roll through synthetic division. We'll drop the first number and go from there. All right, so the last number, -2, is my remainder. I'm going to ignore that. The other values are my quotient numbers. I should technically divide these values by the leading coefficient in the denominator, but notice how that's just 1, so that's not really going to change anything. So if I put the x's back into these quotient values, I'll have a -2 x squared minus 2x plus 0. So technically you don't have to really write that on the end. What's a little different with this slant asymptote compared to the ones that we saw yesterday? Yeah? It's not linear. Okay, notice how this one's quadratic. Kind of interesting. Okay, graphically, I know you might not have a calculator, but I want to go ahead and just show you what this looks like. All right, so what I did is in my y equals, I typed in the original fraction, putting the whole tops in parentheses and the whole bottoms in parentheses. I had to change the window a little bit, but this is what I got. And notice how at the x value of 1, okay, it makes the bottom 0, and if you plugged in 1 up top, it'd be a number. So a number over 0 would be a vertical asymptote. We can clearly see that right here. But on the ends of the graph, okay, we don't level off at a horizontal asymptote, and it's not exactly a line like we saw yesterday. Can you see the parabola shape in there? Okay, so the slant word might be a little confusing because when you hear the word slant, you kind of think of a line, but we're just using the word slant to basically mean non-horizontal. So you could have a line, okay, that's not horizontal, some type of diagonal. You could have a quadratic, it could be cubic, it could be quartic, it could be any shape, okay, it's just not a horizontal asymptote. So let's check this out. What if in y2, I wanted to type in this parabola that we found? Okay, if you kind of watch it carefully, it's so close on this side, it basically traces over itself. And then you can see it kind of come down over here and then trace itself again over here. So that parabola we found seems to be the asymptote that we are approaching on the ends of the graph. So there are some other types of slant asymptotes out there that are not lines. Okay, more often than not in here they're going to be lines, but I just want to show you how there are some other cases. Can we see that? Understand that? Okay. Let's move to the one to the bottom. Okay, how is this one a little bit different than the other ones we've been working with? Yeah? It's factored in the top, okay? Now maybe it would be in our best interest to expand it. That way we can actually determine the degree of the top and bottom. And from there, maybe we can go ahead and set up synthetic division if we have to. So let's go ahead and expand the top. Like go through a FOIL process, see what you get in the end. So I think we'll get negative 2x squared minus x plus 6. Okay, if you go first, outside, inside, last, combine like terms, that's what we'd get. So looking at our powers, we have a quadratic up top and a linear on the bottom. So the top is definitely greater than the bottom. So that's signifying we have some type of slant asymptote. Now, can we think about what the slant asymptote would actually look like? Would it be a line? Would it be a quadratic? Would it be a cubic? Can we maybe anticipate what it should be? Think about the equation we started with up top and why maybe that resulted in a quadratic. What do you think, Noah?
It's going to be linear because you only have a degree of 2.
Okay.
Versus a degree of 3 on the top.
There we go. So we're starting with a cubic, but we're dividing by a linear. So we're starting with 3, and we're basically dividing by a 1, so that would bring us down to a 2. Okay, right? Don't you like subtract powers when you divide? Kind of a similar process here. So if we're starting with a quadratic and we're dividing by a linear, we're starting with a 2, we're dividing by a 1, that would lead us down to a 1, aka a linear slant asymptote. So maybe we'll go ahead and anticipate that. So let's set up our synthetic division. Number that would make the bottom 0 would be negative 1. And now that we expanded the top, we can go ahead and write in those coefficients to help us. Okay, so drop the first number, and we can go from there. All right, I'm going to ignore the 5. That was my remainder. My quotient values are negative 2 and 1. I technically should divide by the leading coefficient of the denominator. And notice how we do have something in this case. We have a -1 out front. So I got to divide those by -1. So it looks like our slant asymptote would be 2x and then -1. If you wanted to time or take the time to actually graph it, okay, see if that slant asymptote makes sense, you could, okay, if you have a graphing calculator, but I think we'll trust our gut with that. Do you guys think you can try the next two? Okay, try the other ones, see if you can figure out where the slant asymptote is located. All right, how about 1/2 x plus 3 for the first one? Sound good? And then 1/2 x minus 7/2? Yeah? Perfect. Okay, we want to go over any piece of those though? Confident and comfortable? All right, let's go ahead and take a look at a graphical example. We had a few yesterday, but we'll try to do one here today. We have a picture as well as a function, and I want us to find the equations of all the asymptotes. Okay, vertical, horizontal, slanted, whatever the case may be. So before we actually try to tackle the equation, maybe we can label what types we should actually be looking for. Can we tell based off the graph what types of asymptotes we should have? Can you find a vertical imaginary line somewhere, a horizontal imaginary line, a slanted imaginary line? What do we notice? Yeah? Okay, so definitely have a slant. Maybe we'll try to draw that in. Any other ones? Go to Olivia. Vertical, -2. Okay, so the vertical one I think is pretty simple to find. Okay, at least in terms of its location, x equals -2. The slant, on the other hand, we're going to have to go through the actual function to help us figure out where that is. I tried to draw it in there, but notice how that was just a guess as to where it is. I don't really know if the y-intercept is 1/2, if it should be at 1, if it's somewhere else. So this is just a rough estimate as to where it should be, but we're going to try to find the exact equation of it based off the function. Okay, so looking at the equation, clearly -2 makes the bottom 0. Makes sense that there would be a vertical asymptote there. The top degree is more than the bottom, so we definitely have a slant asymptote going on as well. Let's see if we can go through kind of the synthetic division like we did up top to help us figure out this slant asymptote. So -2 is our outside value, and then looking at the coefficients, we can go ahead and fill those in. All right, let's drop the first number and go through division. So it looks like I'm going to ignore the remainder of -6. I do have some quotient values, so I can put the x's back into that. I also have a leading coefficient in the denominator, so I'm going to have to take those quotient values and divide it by that 3. So it looks like our equation is y equals -2/3 x plus 2/3. Bless you. Okay. So even though the line I drew in was an estimate, we actually figured out the exact equation of that line. Seems to check out visually because my y-intercept seems to be 2/3. Looks like we did something good. All right, so kind of a review of slant asymptotes that we talked about yesterday. What we're going to spend the rest of the day doing is taking a look at some free response questions that's going to bring all these characteristics together. So restricted values, x-intercepts, y-intercepts, holes, vertical asymptotes, horizontal asymptotes, slant asymptotes, all these different possibilities. All right, so on the next page, all we have to go off of is a picture. We're going to try to pick apart different characteristics, and eventually, if you read the question at the bottom, our goal is to write the equation of this graph. So we're going to pick apart all the characteristics that we've been discussing and use those to our advantage to help us write the equation. Okay, so let's think about some of these characteristics. What can be said about the degree of the numerator, meaning the top, compared to the degree of the denominator, meaning the bottom? Can you think about what characteristic of this graph we should be looking at? Which characteristic is related to the degrees? Yeah. A horizontal asymptote. Okay, so looking at the graph, here's our horizontal asymptote. There's something special about that horizontal asymptote that should tell us about the degrees of the top and the bottom. Yeah? How'd you know? Okay, so it's a horizontal asymptote, and if that's the case, then the top is either less than the bottom, or the top is equal to the bottom, because if the top was greater than the bottom, we had a slant. Okay, so these options produce a regular horizontal asymptote. How'd you know it was equals and not less than, though? Yeah, Lizzie, how'd you know it was this one and not this one? That's the difference. Okay, so this one is always at 0. This one is always at a different number. Okay, so it seems that they should be equal. We'll say because the horizontal asymptote is at a y value other than 0. Okay, so we don't know if the top and the bottom degrees are 3 or 2 or 5. We just know they're the same. Okay, we don't really know what the number actually is, though. What about the one to the right? Kind of related question. If A is the leading coefficient of the top and B is the leading coefficient of the bottom, what do we know about their division? If we were to divide the leading coefficients, do we know what number we'd get? Yeah. How'd you know? That's where it's located. Okay, so not only can we use that the top is equal to the bottom because of the asymptote location is other than 0, but we can also use its exact numbered location in terms of the division of the leading coefficients. So we'll say because the horizontal asymptote is at y equals 1. So again, we just know if we divide them, we get 1. We don't know if it's 3 over 3, 2 over 2, 5 over 5. We just know that the division should give us 1. So it's a little bit vague as to what these values could be, but at least we have this characteristic that we should know is true. All right, let's try the next one. What factors are guaranteed to be in the bottom of our function if we actually had an equation? Can we figure out what factors would be in the bottom? What do you think, Lizzie? Why? Okay, x equals -1 is a vertical asymptote. So the related factor would be x plus 1. Any other places? Good, Olivia? Okay, x equals 2 as a whole. So the related factor would be x minus 2. Okay, so we're basically trying to find those restricted values, a place that makes the denominator 0, aka you have a factor down there. So we're going to look for those vertical asymptotes in holes, where a place on the graph where we don't have a physical point. If we keep this idea of factors going on here, what factor is guaranteed to be in the top but not the bottom? Meaning it doesn't cancel out, but you do have something up top, yeah?
-4.
How'd you know?
Because it's the root.
All right, x equals -4 is an x-intercept. So that means we'd have a 0 up top, but a number on the bottom. So the related factor would be x plus 4. All right, next one. What factor is guaranteed to be in both the top and the bottom? So if it's a factor in both places, that's kind of signifying a 0 over 0. Can we find it? Same idea, Olivia? There we go. Why? That's a whole. There we go. All right, so 0 over 0, we talked about how that's kind of signifying a whole location. So the related factor would be x minus 2. Looks good. What factor is guaranteed to be in the bottom but not the top? Because it wouldn't cancel out. So if it's a factor in the bottom, it would be 0. If it's not a factor in the top, it would produce some numbered value. Go ahead, Elsie. X plus 1, how'd you get that? It's a vertical asymptote. Okay, so with all these different characteristics that we can identify from a graph, we're starting to make the connection to the equation. So let's see if we can go there. We have all this information. Let's go ahead and try to figure out what the equation would look like. So looking specifically at the factors, we know that x plus 1 and x minus 2 should be in the bottom. X plus 4, since it's an x-intercept, should only be up top. If x minus 2 is a whole, it should be in the top and the bottom. Now we already have it on the bottom, so we'll go ahead and write another one up top. And x plus 1 we said should only be in the bottom, and right now that's true, so we don't really have to do anything else. So here's an equation for the graph in factored form. Let's go ahead and expand that into standard form. Okay, get rid of all the parentheses. So if we did kind of a FOIL distribution here, we get x squared plus 2x minus 8, and then x squared minus x minus 2. Is there some way, I want us to think of probably two reasons. are there two ways we can check to see if this equation we produced is actually correct based off the graph that we have? Are there some additional characteristics that we can identify to maybe check our work? Does this standard form equation confirm anything that we previously said? Does this standard form equation maybe confirm other characteristics based off the graph? Can we find some ways to check our work? What do you think? Yeah.
The degrees are equal, which is what we said they were, and then when you take the leading coefficients divided, you get 1.
Okay, Hadley, were you going to say the same thing?
Can't you find the y intercept?
We're going to do both. Okay, so I'm going to come back to you in a second. What did you say, Noah?
The degrees are equal, so whenever you divide the leading coefficients, you get 1.
There we go. Perfect. Degrees equal, okay, power of 2, just like we said in the first question. So if we take the leading coefficients and divide them, we should get that horizontal asymptote at 1. So degrees equal and horizontal asymptote at 1. Okay, so our standard form equation actually confirms the results we said in the first two questions. So far, so good. Hadley, what was yours?
For the y intercept, can we divide the constants to get it?
There we go. All right, so -8 divided by -2, those constants, we get a value of 4, and graphically this should represent a y-intercept. All right, and looking at the graph seems to check out a y-intercept of 4. So I say we did this pretty good. Okay, everything's checking out, everything seems to make sense. The holes are in the right places, the vertical asymptotes are in the right places, y-intercept in the right place, everything's good to go. All right, let's check out another one. This one's a little bit more in a free response format, like we've seen on quizzes and tests this year. All right, a rational function is given and is such that y equals -2 is a horizontal asymptote. All right, why does the provided equation support the fact that there's a horizontal asymptote that is not on the x-axis? Basically telling us there's a horizontal asymptote somewhere else. What do we need to try to look for to see if there's a horizontal asymptote that's not on the x-axis? Do you have an idea, Noah?
Well, the degrees would be equal.
How do you know?
Because they both only have like x times x, so the highest power that's going to get is x squared.
Okay, so if we maybe actually multiplied this out, maybe we'll do this over here, we'll have ax times x, so ax squared, ax times -2, okay, -2ax, -3x for the insides, and then plus 6. If I multiply the bottom out, I'll have x squared plus x minus 6. But with that 2 out front, I'd have to distribute that in. So this really would be 2x squared plus 2x minus 12. Okay, so by actually expanding it, you're confirming what Noah said. Notice how the degrees are equal. So we should have a horizontal asymptote somewhere other than 0. So degrees are equal, meaning the horizontal asymptote is somewhere other than 0. Now that we know that, can we figure out the value of a that's kind of missing in that equation? We know the horizontal asymptote is somewhere other than 0. They actually specify that it's at -2. Can we figure out A? What do you think? Yeah.
-4.
How'd you get that?
Since the horizontal asymptote is -2,
Mm-hmm.
you need to find a number divided by 2. It gets you -2.
There you go. So if we actually divided the leading coefficients, okay, A divided by 2 should give us the horizontal asymptote location, which they tell us is -2. So simply multiply the 2 over and you'll get that -4. Notice how that might be a little difficult for us to understand if we left the function in factored form, because the leading coefficients can be a little confusing. So that's why I suggest expanding it. That way you can see it in standard form. Okay, so you can rewrite them either way. How are we doing? Hanging in there? Okay. Let's check out C. Does the graph have any vertical asymptotes? Why or why not? If any vertical asymptote exists, what are the equations? All right, so either looking at the factored form or maybe the expanded form. How about we just go ahead and put in -4 for A? That might help. Can we identify a vertical asymptote somewhere? What do you think, Blair?
X minus, -3.
Why? That's good.
Because there's a 0 there.
Okay, so if you plug in -3, it would make the bottom 0, but not the top. So I would accept a reasoning because this would produce a number over 0, if you want to use that reasoning. You could also say because x plus 3 does not cancel from denominator. Okay, one is taking kind of a numbered approach, whereas the other one is taking an algebraic approach. Either way, I would be okay with those. So even though we don't have a graph, we can visualize where a vertical asymptote would be. What about D? Can we find any holes? What do you think, Lainey?
Yeah, because X minus 2 is on the top and the bottom.
Okay, so we'll say because x minus 2 is on top and bottom and would cancel. Okay, that's kind of an algebraic approach. You could also say because the x value of 2, if you plugged it into the equation, would produce 0 over 0, signifying basically that you have the factor on top and bottom. So they mean the same thing. It's just the wording or the phrasing that you want to use to go about justifying your answer. Okay, either one. How do you think you would have done on that question? So-so? Okay, I think the top 2 would have been a little tricky. Bottom 2, probably a little bit better, because we've spent more time talking about those. Okay? We're going to do a lot more of these as the unit continues. So we're basically done looking at characteristics. We're just going to practice from now on bringing all of them together. So a little tidbit today, but we'll do more as the unit goes on.